Hello, our fellow learners. Welcome back to the Open Polkadot Bootcamp. Today we're gonna learn about a very interesting topic, and it's also a very heavy sections about cross-chain communication with XCMs. And we're gonna learn everything that you need to know about XCM and also how that you can configure your parachains to use XCM and how you can use XCM to communicate with other blockchains. So before we go to the XCMs and also what is XCMs, we want to the reason why that we need XCM is, let's say, do you remember the visualization that we have for the Polkadot network? That we have multiple parachain connect to the Polkadot relay chain. Then the question is how the two parachain in the same network can communicate with each other. Let's say if you want to transfer the token from this parachain to the another token on the another parachain in the same network, then how can you do that? The answer to that is XCMs, or we also call it cross-chain consensus messaging. In other blockchain network, let's say if you have a two layer 1 blockchain and you want to transfer the token from chain A to chain B, the way the bridging solution brings to you is they're gonna burn the token from the chain A and then mint the token on chain B, and there's never an actual transfer happen between the burning token on chain A and burning and mint and transfer that on the chain B, but it's actually just burning token on chain A and minting token on chain B. The process here, it must be secure by the state proof verifications. So as we already learned that the state machine of the blockchain is actually under the hood has a Mongo tree that to record on the state changes, and in that way the chain B must know the state changes of chain A, and then chain A also need to confirm the state changes of chain B. So that these two actions already done successfully. Bridging on Ethereum layer 2 is the process of burning minting token to L1 and L2 smart contract with state proof verifications between the two chains, and liquidity is managed by multisig. However, XCMB is a cross-chain messaging protocol that inside in the protocol of Polkadot to transporting the messages between the parachains. So in the day zero design, the XCMB protocol is already in the native design of Polkadot, so in that way it's be more secure and easier to scale. Now we're gonna learn about the XCMs. Before we go to this visualization, I'm gonna bring some theory here first. So XCMs stand for cross consensus messaging, and we must understand that XCM is not a protocol, but it's just a language format, and it's bring the intention that between the communication between the consensus system. Consensus system right here mean a blockchain. The power of XCM is XCM enable different consensus system to communicate with each other. Common cross consensus use cases include sending token between blockchains, locking assets on one blockchain in order to gain some benefit on a smart contract on another blockchain, calling specific functions on another blockchain. So these are just few basic examples, and once you can communicate with other consensus system, you can create application that can leverage multiple blockchain capabilities. The potential it provides is especially evident in an ecosystem of highly specialized blockchain like Polkadot. Decentralized distributed systems are very complex, so it's easy to make errors when building interaction between them. So XCM is meant to be used by developers to package this interaction into their runtime logic before exposing that functionality to end user. Reason why we need cross-chain communications is very understandable. That right now we have thousands of blockchain out there, and for every blockchain, the core part of the blockchain, aside from the data, the user, is also the liquidity. It's gonna power the change with multiple actions like the economic model and also DeFi applications. And when you have a new blockchain, you don't want to build the liquidity pool from scratch. But in that way, when you build on Polkadot, you can also ask for other parachain user to use your blockchain and bring the liquidity from other blockchains to your new blockchain. And that is how the XCM's power. We're gonna learn about the architecture, the attribute, and also how you can use XCM in real world. So the question is why don't we just use a native transaction format as a language to communicate with other blockchains? So let's say parachain A can just use the transaction format of parachain B to ask the parachain B to transfer to transfer between the chain A to chain B. Why don't we do that? But why we have to come up with a new language? So the reason behind that is every blockchain, especially like application specific blockchain like Polkadot, like Polkadot parachain, all those blockchain gonna have their own use case, and sometimes they're gonna like update and also like make changes to the transaction format. And not every like parachain gonna have like the same transaction format over time. Not only like in the space, but we also have the time here. So let's say like in the next 10 years, so if the parachain update their structure, or like there's a new upgrade on the Polkadot protocol that affect this transaction format, then like later when you send like the same binary code, it's already like point to the different different message instead of like the one you want to call to the parachain B when the parachain B upgraded. And that is how like when the message format changes, it's also like make an impact on like the message that you want to send for the cross-chain communication, and that's not a very ideal way to do that. So what is the proposed changes? The proposed changes that the Polkadot bring to us is XCMs, and right here we have the XCM executor. Right now we don't have to understand what is XCM executor yet, but let's say like the XCM is a language, and right here you have the interface, you have like the language. You send the instructions from the parachain A with the request like send transfer, and it's translated into the XCM instruction and go to like the binary, then like go to the XCM executor. And the different things right here is that like every parachain can have like their own XCM executor, and the XCM executor is configured by the parachain. So in that way, like doesn't matter like what kind of message that the parachain A send to you, it might be like different, but like at least like if follow the rule of the XCM executor or the parachain B, it can always like point to the like correct message execute transfer right here. So let's imagine like the XCM executor is a translator of the XCM message sent across the blockchain. First, before we go to like some other part of the XCM, I also like want to mention about these 4A of the XCMs. So in XCMs there are 4As. It's also like some like 4 core attributes of XCMs. The first one gonna be like asynchronous. So asynchronous XCM messages in no way assume that the sender will be blocking on its completions. So whatever the message that you send to the parachain, and even like if fail, it's never like hold your runtime. The second point would be like XCM messages are guaranteed to be delivered and interpreted accurately, in order and in a timely fashion. So assume that like all the configurations are correct between like two parachains with an XCM executor, and also like all the configuration required. So one of the attributes of XCM is that like it's going to be like absolute. That means like XCM messages are guaranteed to be delivered and interpreted accurately, and it's guaranteed to like, doesn't be like faulty or like bring any problem if it's like follow the correct configuration. The third point would be like asymmetric. So XCM by default do not have the result that let the sender know that the message was executed correctly. If result are needed, a new message must be sent. That means like it doesn't like it's not like unidirectional message that like you send one from yourself asking like hello, and then like the other one gonna respond back like hi. It doesn't work like that. But like in XCM, like you can only send hello because it's asymmetric, and if you want to receive the result back, then like you also have to send another message to ask for that. And the final point of the 4A would be like agnostic. XCM is not designed for any like specific consensus system, but like any like system that can use like XCMs to for cross-chain communication. They can like build their own XCM executor to handle all the requests. So XCM like make no assumption about the nature of the consensus system and between like which the message are being passed. So XCM should be usable in any system that derive finality to consensus. And for all the format of the XCM, you can like find the format of the XCM on GitHub. It is open source. So right here you can find like the background of why like you need like a language like XCMs, and also like all the core part of the XCM like a transport protocol. Then like, you can also like learn about the XCM communication model that I just go through, like why you have like the 4A and what is like all the 4A. And here like there's also some note about this 4a. So if you want to make some extra reading to understand more about XCM, you can definitely go to that. Then like there's also a few other things like the XCMVM, XCVM. We're gonna learn about that later, and also like the document structure. And here are a few other core part that we're gonna visit later. So I'm gonna keep the document right here. Now we go back to the visualization. And one thing that I must say again, that XCM is a format and it's not a protocol. So XCM just describes how the message should be structured and contain instruction that convey on-chain actions that message intend to perform. It doesn't like process and or perform any action to transfer the message across the exchange. So it's just a very high level language. The other part that are gonna handle the process of transferring your token or transferring your NFT across the blockchain or perform any cross-chain actions gonna be the transport protocol. So now we're gonna visit the transport protocol so that we can understand more about that. So as you can see right here in our visualization, we have the front end and the back end. So imagine like for the front end, the XCM interface, we also have another palette called the XCM Builder palette that you can use the XCM Builder palette to build the XCM message, any required XCM message to send to to other blockchains. And we also have a contract environment recompile built-in that you can also add to your blockchain to support this XCM interface. Two ways that you can also call to the XCM to the runtime and also to the smart contract. So after the front end, we're gonna definitely have the back end. And then when you have the XCM right here, which is the extensible language for communication between the consensus system, power the XCM language and to transport between the consensus system, we're gonna have a transport protocol. So this transport protocol gonna compile, combine different pieces in to transporting the message. So the three core things of the XCM gonna be like XCMP, UMP, VMP, and also like HRMP, but I don't have it here. They also like bridges and custom relay as well. That can be supposed to be a transport protocol, but these inside the Polkadot network that to communicate across the blockchain, you're gonna have like XCMP, UMP, and VMP. So in the Polkadot wiki, XCM transport method right here is described very details like what are these transport protocol. So with the XCM formats established, so common pattern for protocol of this message are needed. So Polkadot implement two message passing protocol for acting on XCM messages between its constituent parachange. So there are three primary methods for message passing. Those are XCMP, cross consensus message passing, HRMP, horizontal relay routed message passing, or we also call it as like HRMP or XCMP Lite. The reason why we call it SRMP Lite, so before the XCMP is established between two parachange, HRMP channel must be open to establish this first. So it's like you want to let these two parachains to know each other first before we establish the trusted communication between them. VMP, vertical message passing, and we're gonna learn about each of them one by one. So for the XCMP, XCM is related to XCMP in the same way that REST is related to RESTful. So cross consensus message passing, secure message passing between parachange. There are two variants, direct and relay. So with direct message data goes directly between parachain and is constant on the side of the relay chain and is very scalable. That means like two parachain can directly communicate with each other and doesn't have to go to the parachange. With relay, message data is passed via the relay chain and piggyback over the VMP. It is much less scalable and on-demand parachain in particular not receive message due to excessive queue load. So in this case, like, you might not need like a third-party consensus system standing between, or we can call it a relayer. So right here is our relay chain that stand as at the middleman, like relaying the message between the two parachains. So right, instead of like establish a direct communication channel between the two parachain, you can also rely on the relay chain as like the guy standing in between to establish the communication channel between these two chain A and chain B. That's what we call a relay. So cross-chain transactions are resolved using a simple queuing mechanisms based around a Merkle tree to ensure fidelity. It is the task of the relation validator to move transactions on the output queue of one parachain into the input queue of the destination parachain. However, only the associated metadata is stored as a hash in the relation storage. We can also discover about this queue later when we try to configure the XCM executor. So for the VMP, so VMP stands for vertical message passing. Vertical message passing passing between the relation itself and the parachain. That means why it's called vertical, because let's say that a relation is a blockchain right here, and if you want to communicate with that, like a parachain have to send the message upward. That means like vertical. And we also have downward. That means like how the relation can communicate with the parachain by sending the message downward. That is also like vertical, which is like different side. So that's the reason why we call it vertical message passing. So right here is included UMP upward message passing from a parachain to the relation, and downward passing from the relation to the parachain. And HRMP channel or XCMP Lite. So why XCMP is still being implemented? A stopgap protocol known as horizontal relay routed message passing HRMP exists in its place. Why it's called horizontal? Because right here you can see like it between like two parachain in the same level, not like with the relation. So that's the reason why it's horizontal. And HRMP was the same interface and functionality as XCMP, but it's much more demanding on resources since it stores all the message in the relation storage. So when XCMP has been implemented, HRMP is planned to be deprecated and phased out in favor of it. So that's also the reason why we call it XCMP Lite. So it's only stand temporarily to set up the communication between these two chains until the XCMP ready. So when XCMP ready, then like HRMP can be like removed and it's become like deprecated and no longer needed. Right here, there's also like a few things about the XCMP. So for about the XCMP, cross-chain message will not be delivered to the relay change. Cross-chain message will not be constrained to the maximum size specific in byte. Parachains are allowed to block messages from other parachains, in which case the dispatching parachain will be aware of this block. So collator nodes are responsible for routing the message between the chains. Collator produces a list of these messages, so it's input-output. And on each block, parachains are expected to route messages from some subset of all other parachains. So when a collator produces a new block to hand off to a validator, it will collect the latest address queue information and process it. Validator will check the proof that the new candidate for the next parachain block include the processing of the inspected address message to that parachain. So right here is a very low level design, also the stuff that like how this message can like be transported across like using the XCMP. And actually like most of the time you don't have to care about it, but we're gonna still go to this Polkadot wiki so like we can understand it fully. Okay, so right here is already about all the things about XCM transport. We're gonna go back to our Escalibur architecture and we're gonna dive deep into other things. Now, after we already solve the transport protocol and we already understand like what are like some of the transport protocol used in the XCM and how like the message gonna be passed between like parachain and relay change. Now we're gonna go to cross consensus virtual machine. This is XCVM. So XCVM is also like an important core. It's also a core component of like all the knowledge about like XCM as well. In XCVM, there are a few things. First about the instruction, and the second one register. So XCVM, this virtual machine is a register-based virtual machine, and it accepts the instructions and then process all the instructions and add that to the register add that to the register along like the instruction process, similar to any like kind of CPU. In our CPU, we also have a list of new instructions we pass to the CPU. It's gonna process and it's gonna like do all the actions that the instruction provided. That's the reason why the CPU is called processing unit. It's also similar to this virtual machine. Now you might wonder like what are those register and also like what are these instructions, and we're gonna visit back the XCM format, and in the XCM format you're gonna find like the XCVM register. So in the XCVM register contains several machine register which cannot generally be set at will, but rather begin with specific value and may only be mutated under certain circumstances or obeying certain rules. So different from like the CPU, different from like our computer, and also like traditional virtual machine. So XCVM is designed to be like not very flexible in terms of mutating the data of the register, and there's some set of register must be used at specific location. So there are a few register right here. There are 11 register in total. The first one is going to be the program register, then program counter, error handler, appendix, origin, holding, surplus weight, refunded weight, genset stated topic, and each register right here also have the description why you need those. But we're gonna go to this. So let's say, for example, the origin register. The reason why you need the origin register is so when you send a message from the person A, then the locations of the person A, or we can select the current location, which is the person A, going to be stored in this origin register. For the holding register, so all the amount of the current relative locations that is held by the interior system and not has like on-chain representation yet. So let's say if you want to transfer from chain A with like the 50 tokens from chain A, then it's going to be pushed to this holding register, and then later it's going to like be like ring back and then like deposit to like the chain B, which is the chain that you want to deposit to. Surplus weight register, amount of weight by which an estimation of the original program must have been overestimation. We're gonna learn about these register later when we come to like some core instructions of the XCVM. But let's say there's also a few other base register right here. For example, like the program register. So currently executing program of the instruction of the XCVM. So when the XCVM go to the list of instructions, it's gonna like pick like each instruction and gonna push that into the program register. Then like the program counter register gonna be responsible for like increasing the index of list of the instructions. So let's say like, if you have like 10 instructions, and when it's processed the instruction A, that instruction A gonna be pushed to the program register, and then the program counter gonna be increased by 1 until like at the end of the list of the instructions. For the error register, information on the last node of error will happen during the program execution. Error handler register, any code which should run in case of error. So when there's an error happen, you want this handler register to be processed, the code is added, it's like a callback. And appendix register, any code which should run following the current program. It's also some kind of other like event callback. So right here I have the XCM workshop from South Tabrizi again. Shout out to Sean. We already mentioned about Sean once, but here also the resource that he made for the XCM instructions. So the XCM instruction basically a vector of the struct instructions, and these struct instructions that you can see right here, there is accept the generic type call inverse, and then with a list of all the instructions. I think that there are more instructions than I expected that I added in the visualizations. And there's some kind of instruction like the withdraw asset, like that you withdraw the asset from the chain A, or like any like a specific consensus system. Also like genset, that like here that you interact with a runtime call from any consensus system as well. It's in encoded bytes. Then the clear origin, that you want to remove the origin from the VM. Clear error, remove the error. Or we also have the claim asset, that when you claim the job asset back when you cannot send the asset to the chain, to the destination chain, then you can also send an instruction to claim it back. here. So that's the reason that the list of some of the instructions in the code base of Polkadot SDK. As always, whenever we learn a new topic, we should open the Polkadot SDK. You're gonna find the XCM executor in XCM Polkadot XCM. Last time we go to the frame, right? When we want to learn about substrate frame library, right here we want to learn about XCM. So there's XCM executor under the XCM library, XCM folder. Anything about XCM gonna be right here. So XCM executor gonna have this process instructions, and you can see this process instruction gonna like go to each instruction one by one, go to the vector of instruction that we just work to in the last minute, and it's gonna process the instruction one by one. Then right here it's gonna match each instruction with each order, and then like process the logic one by one. So you can see it's processed the withdraw asset, reserve asset deposited, transfer asset, and transfer reserve asset. We're gonna visit this instruction later when we learn about all the high-level concept. Okay, so now we already done with the XCVM. We know that like instruction gonna be the input added to the XCVM from the XCM language, added to the XCVM, and then the XCVM gonna use the register as a register-based machine to handle along with the logic processing the instruction using the method called process instructions in the XCM executor code that we just saw. Now there's another one right here, that is the XCM executor. So XCM executor standing along with the XCM virtual machine is also like one of the core part of the XCM virtual machine. Imagine like the XCM virtual machine is a computer standing on this level, and it's for like every process happen during the instruction processing, it must like have like the one executor to store and also like to do any extra actions needed. So that's the reason why we need the XCM executor. So here's also like the structure of the XCM executor, that you have like the holding, origin, original, origin, shader, or error, total surplus, total refunded, error handler weight, appendix, and appendix weight, all similar to the instruction that, and also the register that we visited. And to configure the XCM executor for the runtime, you're gonna need the XCM configurations. And here like the list of all the configuration of the runtime that we're gonna visit later. And that is like the overall architecture of the XCMs.